All right, good morning, everyone, and thank you for coming to my talk. I'm really excited to be here this morning. Before I get started, I wanted to poll the audience a little bit and get to know you guys and what your interests are. How many people here are practitioners of artificial intelligence, machine learning, people who are out here implementing systems? Raise your hand if you are. Excellent. How many people are more on the business side trying to learn about what AI can do for you and your business? Roughly about half and half. Great. I'll try to address both of these in my talk as I go forward. Thank you all. I'm Catherine Havasi. I'll tell you a little bit about my background so you understand a little bit about the perspectives that I'm bringing to what I'm going to talk about today. So I'm CEO and co-founder of Luminoso, which helps large companies make sense of their customer feedback data through advanced natural language processing. I also run ConceptNet, which is one of the world's largest open data projects that's been collecting information that people know and computers don't and releasing it as a knowledge graph on the web for, at this point, many years in many different languages, including English and Japanese. So and before that, before Luminoso, I taught at the MIT Media Lab where I directed the Digital Intuition Group. And through all of these, there's sort of been this common thread of helping computers understand the world more like a person and less like a machine. So today, we are, at the same time as this talk, we are at AAAI, which is the big AI conference in California, releasing some new machine learning and some new open data that might be useful in Japanese as well as in English. And I'm also going to be telling you about that today and about some of what we do to make that work, and also about how you can use it and how you can use the concept of common sense to make your businesses smarter. All right, so I don't need to tell any of you that there's been an explosion of data in the world. We are creating more and more information on a daily basis, and there's a lot that can be gained by the information and the digital breadcrumbs we leave behind as we go about our lives, using the internet, talking to brands, and interacting with each other online. In order to really make use of that information, we need to have a very deep intuitive understanding of the language that's used and the nuances and the expressions we have. When we communicate, we use everything from slang, jargon, very technical corporate terms, emoji, cow emoji, all kinds of things, figurative language, to be able to make and communicate the stuff we want to be talking about. This kind of language has been traditionally very difficult for computers because it's very hard, it takes a lot is unsaid. And so what we want to be able to do is take that information and build natural language processing that's able to capture that and make it easier for computers to use. Traditionally, one of the reasons why this has been so difficult and why many machine learning techniques have not done as well for natural language processing as they have for image recognition and other big data problems is because the language we use when we talk is very creative. Whether or not we're discussing global politics or we're discussing a product that broke that we're upset about, we use really interesting language to describe the problems that we have. And there are a couple different reasons for that. Well before Twitter, we were very motivated to be able to be creative and exciting and interesting in the language that we use. So in a sense, Twitter really tapped into something because when we're out there, we're writing interesting tweets, we're looking to get retweeted, it's tapping into something that psychologists have known for a long time, which is that we feel we're going to get our point across to a larger audience when we're more interesting, creative, funny, all of these things in the communications we have. And a lot of modern psychology research in the way people communicate online has pulled out all of that information as well. So that's why we're so interesting and so creative when we speak using the internet or using electronic devices. The other problem that we have that's inherent in the way language is used online is that we're very concise. Now, I know that 140 characters, you can say a lot more in Japanese than you can say in English or German or many other languages, but it's still very, very abbreviated. And even before then, there was a lot of work that's being done saying that we leave a lot out when we communicate. So if I'm talking to you, I never feel the need to tell you that if I drop something, it falls down. I expect you to know that. I expect you to know that this morning when you went to get your coffee, it comes in a mug. No one needed to tell you to put your coffee in a mug, and you didn't need to tell people that the coffee that you had comes in mugs. These things are all what we call common sense. And that's actually a technical term in natural language processing. It's the world knowledge that we all have, and we all assume other people have. Important linguistic philosopher Paul Grice came up with something called Grice's maxims, which say that this kind of information is routinely left out of discussions we have because we want to not be boring. It's exactly the same as what we were talking about with Twitter. We're concise in our language. We leave out things that we expect everyone to know because we don't want to be considered boring. Both of these two things make language understanding uniquely difficult for computers and uniquely difficult for machine learning algorithms because much of the important glue that's inherent in language is left out of the data sets that you have to encounter. So when businesses started diving into language processing to be able to use automated techniques to make sense of language data, initially we started working with sentiment analysis. Now, sentiment analysis is great. It's the ability to tell whether or not a statement is positive or negative, but very quickly, as many of you might know, you run into the limitations of sentiment analysis. And the reason for that is that it doesn't necessarily address all of the important issues. Knowing something is positive or negative doesn't tell you why it's positive or negative. It also doesn't tell you whether or not you're even asking the right question in the first place. Knowing whether or not something is positive doesn't tell you how to address it or what aspects of it are more positive than something else. So very quickly, people who were advocating for natural language processing began looking for deeper questions and deeper solutions. And we saw the business world change from asking positive or negative to asking for these deeper questions. So the kinds of questions we saw and the kinds of questions we thought people were asking looked a lot more like, how are my distribution channels changing as people are interested, at least in the US, more in local produce and local manufacturing? How, when someone calls my customer service agent, what questions are they likely to ask the agent? These are the kinds of questions people are asking, and they're not questions that have a very easy positive or negative response. And there are also situations and places where people are likely to use creative or exciting language. So natural language processing needed to come up with some answers and some scalable answers very quickly to be able to harness these questions. Now, almost everybody here is probably familiar with deep learning. We talked a lot about it yesterday and about how it's the technology to watch. However, there are some interesting problems with deep learning, and I know the gentleman from Google is speaking after me about TensorFlow and about much of this stuff. It's fantastic, but it has one problem for everybody in this room, which is that it's very difficult to take deep learning and scale it down to the amount of data that you have. So when you're building one of these systems or training one of these networks, you need a lot of information. So let me break down deep learning for one quick second. So in natural language processing, deep learning is part of a type of machine learning called vector embeddings. I know that got mentioned a couple of times yesterday. I don't think it got deeply explained. So the idea of vector embeddings is building a representation where concepts or words or pictures in your space are represented as vectors. And deep learning is a subset of word embeddings for natural language processing. The rest of this talk, we're going to be talking about word embedding techniques as a whole. The problem with embedding techniques and the problem with things like Google's Word2Vec is the amount of data they use. If you think about the rather famous example of AlphaGo, where Google's machine learning, DeepMind's machine learning, was able to defeat a champion at Go, that was very exciting. You know, years and years and years ago, when I was taking AI, maybe 15 more years ago than that, no one would ever have guessed that a computer would that quickly defeat someone in Go. It was a very hard game to do. However, what it took, the amount of data it took to do that, was about 30,000 training, about 3 million digital Go game examples. And after that, they had run out of data, so they had to have the computer play itself in Go. That doesn't work in language processing, because you can't have a computer talk to itself. That wouldn't make any sense. So you cannot generate extra training data that way. So very quickly, it became clear that in order to build embedding spaces and build these kinds of machine learning that works for a business, an individual domain, you're going to need to find a way to scale it down to the amount of data that's actually created. And so that's how we go back to the common sense, because we're going to look and see how we do it as people. So people are able to learn new words and understand the meaning of creative language because we all share this background knowledge called common sense. So we go back to that background knowledge and we use it to fill in the gaps in the incomplete data that we see on a daily basis. And we want to be able to take that and mimic it with the machine so that we can learn this kind of powerful machine learning, vector embeddings, with much less data. And that becomes incredibly critically important. So how do people do it? How do we learn really complicated concepts? So some of you may have seen the linguist George Lakoff publish some books. He is a sort of popular, he's not Chomsky, but he's kind of the level below in writing pop science books about linguistics. And his theory is that we understand complicated concepts by making analogies to simpler concepts. I don't know if this is true in Japanese, but in English, if we talk about information, we often use words for water. We talk about information flow and all of those kinds of things. And so we're making an analogy in our heads to understand information because we can understand water. And if you think about it, much of the way we understand complicated concepts might be working that way. So how about we start looking at all of that kind of thing and see how we can bring it into natural language processing to make these things smarter. But to start with, what are you going to need to know to understand the average sentence? So if I said I went to the supermarket, what kinds of things would you need to know to understand that? You need to know that probably you took groceries, you put them in a cart, you checked out, you exchanged money for goods and services. You probably didn't eat in the supermarket, even if you bought food there. It's different than a restaurant. If I'm talking to you about going to the supermarket, I leave all that out. So that's all common sense. That's the kind of stuff we want to collect and add back into the computer. So let's back up a good number of years into the late 90s at this point. So in the late 90s, I was working in Marvin Minsky's group at the Media Lab, and we were looking at search. So to bring up Google again, in the late 90s, Google had just started in Stanford, and the idea that the connections between links on the web was going to build this graph of trust was not something that people knew about search on the average at that time. So Professor Minsky came up with an idea that was, if we understand the intent of the searcher, then we would understand how to return a web page better, how to search better. And in order to understand intent, we have to understand this common sense. So we started a project where we began collecting this information from volunteers online. In the late 90s, it was very easy to crowdsource. People were very excited to talk to a machine online, and so they would just enter data for us without needing any of Lucas's Crowdflower or anything like that. And so we started collecting the basic things. People want to be respected. Coffee comes in mugs. Things fall down and not up. All of that kind of information in English. And we started building this knowledge base about it in order to make search smarter. Now, it turns out that's not actually, although intent in search is something that's very big right now, in the late 90s, that wasn't the key, right? But we did build this large knowledge base, and we started building it in English, and many years later, we're still building it. And the kinds of things in that, the way the knowledge base works is, luckily, we came up with the idea that maybe this could be a graph with different things connected to each other. So if we think back to the example with the supermarket. So we can think about how to represent the knowledge from that example in a graph. So we have nodes that represent concepts, not words, concepts. And connecting those nodes are relations. The OpenMind project, or ConceptNet, has 21 different types of relations in English. But some differences are okay there. And what we want to be able to do is take these nodes and connect them together. To understand this statement as a graph, you need to understand stuff about money, about how things are paid for, and about what food is used for. And if you think about it, you're soon collecting lots and lots and lots of information that's all connected to each other. And over the past 18 years, that's what we've been doing. We've been collecting this knowledge in many different languages and building the largest open knowledge graph out there. So the difference between us and something like the Google Knowledge Graph is that we only have this common sense. We don't know who's president of the United States. We don't know anything about world politics. We don't know about entities. What's in here is information that is always timeless and always the glue that holds language together. So in about 2006, we had built a pretty large English knowledge base, and we started reaching out to our connections across machine learning to be able to build this in other languages. And we partnered across the globe. Here in Japan, we partnered with Hokkaido University, Unisys, and Dentsu to begin collecting information in Japanese. And we partnered with these other universities as well. And one of the big ways we had to start collecting this information was not just having people enter things in and crowdsourcing. At the time, we started collecting it with what's called a game with a purpose. So people played online games to be able to teach the system information about the world. Many years ago at this point, we ended up with 2 games, one of which is called Nadia. Some people here might have played it. It was somewhat popular, where you end up teaching a young girl about Japan and about living in Japan. The other one was a conversational agent robot game. And both of these let us collect a lot of information. And we used that information, and the information, eventually we began machine reading off the internet. And time passed, and machine reading got a lot better, and computers got a lot faster, and now we have, in about 70 different languages, we have this knowledge graph available called ConceptNet with about 17 million nodes on it. And it's one of the largest knowledge graphs out there. So I invite you all to be able to use ConceptNet anywhere you need a knowledge graph in Japanese. You can go to, and I'm going to turn around so I make sure I get the web address right, conceptnet.io, and download that at any time. ConceptNet has long been affiliated with the Media Lab. As we get bigger, we have become more of an open data project, so we also now have a URL that doesn't say Media Lab on the end of it now, finally. And ConceptNet is browsable online. You can also use our REST API directly to pull down information about terms. Or you could download all of ConceptNet onto your computer. I told you ConceptNet is very large, so I recommend using the REST API. Also at the website, you can access our developer community, where we have a chat room, so people who use Slack, to be able to ask questions and talk both with contributors to the project as well as potential users of the project. We have our code on GitHub, and we can help you connect to other linked data resources. And we have just put out a new version of ConceptNet recently in time for AAAI, the big AI conference in California. So not only is what we're doing building a understanding of the way people's intuition filters back into language, but we also are trying to take that and use it to make computers smarter. We don't want to just build knowledge graphs. We want to build better machine learning. And we want to grab that digital, computerized human intuition and put it back into the machine. So right now, when people do natural language processing, there are two big areas that they tend to work on. So people tend to use a rule-based system, doing ontologies and doing design of that kind of thing to build dictionaries and help computers understand language. That's very difficult because it requires a lot of data and a lot of time to maintain and build the dictionaries. Besides that, the meanings of words change, and the dictionaries cannot keep up without a human in the loop. On the flip side of that, statistical machine learning needs you to have seen everything you are going to see in order for it to know about that. So it lacks the intuition that we talked about earlier. So that's where Luminoso comes in. Luminoso uses, my company uses the common sense backbone we talked about earlier to be able to build domain-specific word embedding systems without a human in the loop from a very small amount of data, the kind of data you actually have. And so we take a background knowledge and we adapt it without the need of GPUs, without the need of clusters, and without the need of lots of training data to be able to help you bring the power of the kind of machine learning that everybody's talking about to your actual enterprise or to your actual project. And then you can learn about language from only a couple of examples. And after having done this, we were founded in 2010. So after having done this for a good number of years, we decided to release some of the background material we've built at Luminoso publicly to help other people use this kind of machine learning. So what we're doing is not releasing the domain-specific or the domain-specialized knowledge. We're releasing domain general word embeddings for different languages, and we'll talk about them. I'm going to skip through this because I'm going a little bit slower. So this week at AAAI, we're releasing what's called ConceptNet Number Batch, which is a way of their basic word embedding models for different languages, including Japanese. So for people who really wish Word2Vec, Google's Word2Vec worked in Japanese. This is that, and it's compatible. And so how we did this was by combining together ConceptNet information about the world, connected across languages with different types of distributional semantic models, and using that to essentially do a transfer learning where we're taking the information that's contained in things like Word2Vec and Glove, combining them together, adding in the common sense, and then using that to build word embeddings in different languages. And we've done this for 70 different languages. It's available online, and it's a domain general background space. And it tests very well. So for example, this is unreleased, but the domain general space in Spanish we've tested actually performs better than if you had trained a neural network in Spanish from scratch on Spanish data. There isn't a lot of word embeddings evaluations in Japanese. So if you know of some, please come find me after the talk. I would love to run them on our system because it is very expensive to build gold standard corpora. So how do you evaluate this kind of machine learning? So we evaluate it in a couple of different ways as a field. A lot of the evaluation benchmarks look at word similarity. So there are things like people taking a test are given 2 pairs of words and asked how similar they are. So we all know that beach and coast are very similar, but cloud and kitten are not. And we can build that knowledge base, that test set, simply by evaluating against these different word pairs. And we can do it for both simple words and concepts that everybody knows, and more rarer, more technical words. So that's the rare words corpora and the common words corpora. And there are a lot of these tests out there, and there are industry benchmarks for how this kinds of machine learning works. And so we are also evaluating against these tests, and we are releasing at AAAI tomorrow performance metrics on all of the evaluation tests. We're the orange bar, which is pretty good. The other exciting thing besides word similarity is analogy. Now, in machine learning, there's been a lot of buzz around analogy-based tests, but a lot of those tests are tests that have been built specifically for testing computers. In the United States, we have a test that people take in high school when they want to go to college. It's called the SATs. You probably have a similar test. And as part of the SATs until very recently, people had to do analogy questions like the one on the screen. Remuneration is to labor, as trophy is to victory. So it's something you get if you did, if you have a victory, you get a trophy. And so being able to understand that kind of thing is important for high school students going to college. So the SAT record for performance for AI on this is about 10 years old by Peter Turney. And previous to this, it used to look up answers on the web as part of the test, which, as you know from taking the test when you graduated from high school, you're not allowed to do. So that was the highest performing AI system. So we're benchmarking now not against the AI tests, but against this test here. And we actually, I don't have that slide here. We actually get the human average college applicant level performance on this test, which is about 57%, which probably says more about high school students than it does about artificial intelligence. But that's pretty exciting for us that we're performing at that level. And so those are some AAAI results here at BDAT Tokyo. So Luminoso takes all of this domain general embeddings machine learning that we talk about and uses it to power 2 products, Luminoso Analytics and Luminoso Compass, which process customer feedback and other kinds of unstructured text data and help take insights from that and put them throughout the organization. So I'm going to take a moment and give you a couple examples. So we were working with a car manufacturer here in Japan and looking at feedback about their cars that had come into dealerships. And we came up with a lot of very interesting insights here, but I think there's one I want to share with you that shows the power of common sense. It turns out people had been coming into dealerships talking about the fact that their cars smelled bad. And they had come up with a lot of different terms for how their cars smelled. They said, it smells like there's a dog in my car, but there hasn't been I don't own a dog. It smells like an attic. It smells funky. They frequently didn't even use the word smell. Maybe they said odor or other words that mean smell. And all of these were getting categorized by customer service agents into other which is that bucket in your call center that you hate, where things that are truly going wrong that you didn't anticipate go to haunt you. And that probably translated very badly. And so what we ended up doing was being able to look into this other bucket and say, all of these people are talking about the same smell, because you and I know that, but the computer needed to know that. And not only that, that smell is very connected to the other people who are talking about the problem of having dew in their car in the morning or condensation in their car. And that information is something that led the computer to put the two things together and conclude there's a problem with a musty odor in the car. The manufacturer was able to look at those models, find the air conditioning hose was coming undone in certain models of the car, water was leaking into the car, causing condensation, causing mold, causing a bad smell, and being able to tell dealerships how to fix this and treat customers who come in with this problem as if they have an actual problem was able to improve customer satisfaction with dealer interactions. Now, of course, there's a lot more stories like this that involve carburetors and steering columns, but they're a lot less fun to tell. Another example on how to use this more on the marketing and less on the customer service end of things comes from a US company that makes men's toiletry products. So those, if you ask a guy whether or not the color of their toiletry product affects the way they buy, they will tell you no. But this company suspected that that was not true. So they put these products in the homes of consumers for a couple weeks, and then afterwards they called them up and said, how did you feel about your experience? Now, the products that they put down, the prototypes, were different colors. And so they were able to use this to measure how different people talked about the future of whether or not they would purchase these products and compare that against the color. So they were able to find that people talked a lot more passionately and a lot more loyally about the product when it was more brightly colored. They were able to use this data to hire a design firm to make a very brightly colored version of that product that you may use, and it became their best-selling product in this line. So those are a couple reasons why you actually need, both of those examples, you actually need common sense and not just statistical data to be able to grab those and pull them in. All right, so I hope I taught you a little bit about common sense and natural language processing. And showed off two open data projects you can download. One, a vector ensemble data set called ConceptNet Number Batch, which does work in Japanese and can serve as a embedding space for Japanese, as well as the semantic network ConceptNet, and told you a little bit about what Luminoso does. So I think I might have time for one question if I'm lucky, but I will be here throughout the day, at least until lunch, and I'm happy to talk to you and give you more information. I'd also be happy to connect you to my co-founder and co-conspirator, Rob Spear, who does a lot of the science work I've been talking about and knows a tiny bit of Japanese, and would be very happy to help answer questions as well. Thank you all. I don't have time for questions, do I? Do we have time for one? One question? One question, which is always the way to get, yes. 1 second, just so if anybody wants, I do have one of these, which means you can ask me questions and I can understand you.
Thank you for your presentation.
Well, that helps too.
I heard you talked about ConceptNet Number Batch, which is a method that takes many different kinds of word embedding algorithms into account.
Yes.
But I was wondering if you also have a good solution to a situation where you have two different sets of word vectors, but they were trained on different sets of documents.
Yeah.
But what I want to do is to combine two different, the two vectors. Is there any good
You have
way?
two vocabulary sets, right? And so
Yeah,
your problem is that you need to align across vocabulary sets. My answer is, and I'm sorry this is my answer, yes, but it's Luminoso's technology, not part of the open source project. I would be happy to talk to you afterwards a little bit about that and maybe some things in academia that might be pointing in the right direction around that. But yes, that's something that we're working on, but you know, it's part of our company's technology.
So you mean is it there is a good way to do that as opposed to perform a
Yeah, there
word-
is a way to do that. There's definitely a way to do that. And you have
Yeah.
to do that when you're building the transfers across languages.
Yeah.
Because if I'm taking Glove and Word2Vec and ConceptNet, you know, I'm expanding the vocabulary back up, but I also need to be able to, the three, even Glove and Word2Vec have different vocabularies, so you need to align across those. And I can probably show you something that aligns across Glove and Word2Vec that will give you some ideas in that direction. And come find me and I'll take a card and send you a paper.
Yeah, okay. Thank
Yeah.
you.
Sorry, that was probably a little fast. I think we're good. All right, thank you all. I'll be around after the talk and would love to talk to you.